Hello everyone, welcome to the 17th lecture of group theory. So in the last lecture before our internal exam, uh, we have seen conjugacy class, right? Conjugate is in this being conjugate is an equivalence relation, and we have seen the class of A, we have seen normalizer of A, and the relation between the number of conjugates. In fact, the number of conjugates is same as the number of distinct right cosets of n a in G. So that we have seen, and then that gives us the class equation, which looks like this. So if G is a group, and then order of G, that is summation CA. This is what we have seen, but this is same as we have seen that summation order of G upon order of NA, where A is not for all A in G, but where the sum is over, sum runs over exactly one A in each conjugacy class of G. So this much we have seen, and where NA is this, NA is normalizer of A, which is all those elements which commute with A. So N all X in G, so that XA equals to AX, right? See now what happens if NA equals to G. NA equals to G, that means every element of group will commute with A. Or in other words, we say that A commutes with every element of uh, the group G. So A belongs to the center of G. So recall what is the center of G. We denote by ZG, or we just denote by Z, and this is all those X in G, such that for every Y in G, XY equals to YX. So here this is the difference. Here X in G, so that AX equals to XA. That means those X which commutes with A. Here we are taking those X which commute with every other element of the group, right? So if we consider NA equals to G, then what happens? This implies XA equals to AX for all X in G. So that means A commutes with every element of G. Right? So if every element of G commutes with A, XA equals to AX for every X in G, we say that A also commutes with every X in G. So all those elements which commutes with every other elements of the group that is in the center. So we can say that A belongs to the center of group. A belongs to ZG. Right? And conversely, also this is true. If A belongs to ZG, then AX equals to XA for every X in G. That means A commutes with every element of G. That means every element commutes with A. That means that every element belongs to an A, and therefore NA equals to G. So what we have, let me state as a lemma. It's a short result we have. So let G be a group, and take some space here. Oops. Yes, so let G be a group, and A be an fixed element, right? Then we have this A in ZG if and only if the normalizer of A is the whole group G. So in particular, if G is finite, this is true for any group, but in particular if G is a finite group,
then what we have? We have same thing, but we can compare the order. So the order is equal. So in case this case A is in Z center, if and only if normalizer equals to G, and for finite group we can talk about the order. So number of elements in A is same as number of elements in G. Why are we talking about this? Because we are interested in this class equation, this term, order of G upon order of NA, and this will be 1 in that case. So okay, so then the class equation gives, so this is the lemma, and so then we can write the class equation gives or then by the class equation we can write in fact this into two parts. Order of G equals to, here we have summation order of G upon order of NA, right, where the sum is over only those 1A from each equivalence class, and this we can write into two parts. So we take the sum, right? So we take NA is always a subgroup of G, so here I can write order of NA is not equals to order of G, or NA is not equals to G, and here let me write NA equals to G, right? So we have order of G upon order of NA, here also order of G upon, so the same sum I have written divided into two parts, when NA equals to G and when NA is not equals to G. When NA equals to G, this is 1 if G is finite group, so consider G finite, then this term will be 1, right? So that is here I can write, if a finite group, so order of NA equals to order of G, in that case we have 1 plus, and here I can write order of NA is strictly less than order of G. So NA is a subgroup of G, as we have seen earlier. So because it is subgroup, order is either less than that or equals to G. Equals to G we have considered the case. So now if it not equals to G, it should be strictly less than this. So order of G upon order of NA. Right, so we have done nothing, just divided into two parts. That's those ones we are separating. Right, there is possibility that this may be same numerator and denominator, so we'll get 1. Those 1 we are separating out, and other when it is not 1, right, it is a proper divisor, then we write in the other part of the sum. So how many times this will be? Summation 1 1 1 1, how many times it will appear? So there will be 1 plus 1 plus 1 and so on, 1 plus 1 plus and so on plus 1, some so many terms will be there, and then this part as it is, summation order of NA strictly less than order of G, so this will be an integer other than 1. Right, how many times? So as many as times such that order of NA equals to order of G. But this is same as saying that A belongs to ZG, right? Because this is just we have seen here. In case of finite group, we have this. So whenever an order of NA equals to order of G, we have A belongs to ZG. That is what our conclusion is. So how many times 1 will come? As many as A will be there in ZG. So this we can write as, therefore, we can write as order of G. We can write this terms. So I can write order of ZG, because 1 1 1 1 how many times? So this many times. So this many times. So that is nothing but order of ZG. जितने A ZG में आएंगे उतनी बार 1 आएगा, and then this term as it is, order of NA is not equals to order of G. It will be of course strictly less than that. So let me write like this. Okay, so this is now our new modified version of the class equation. And this will be very useful. We'll see two applications today of this class equation. So this is our class equation becomes like this. So we have not done anything new. What we have done is we have just separated out all those terms which are one को अलग से लिखा है, and then so this is also called class equation. Oh, sorry. So if we don't want to write this, we can write this as well, but here it will not be not equals to. It is allowed equals to. So equal to part we have written separately. How many times it will be equal? So that means the number of elements in ZG. So that is order of Z and plus this. So this class equation, this version will be used in applications. So let us consider some application. First application, what we are going to show is that every group of order p square where p is prime, such a group is abelian. Right? So every group of order p square is abelian. For example, groups of order 4, 9, they are all abelian. 4, 2 square, they are abelian. Groups of order 9 is always abelian. Any group of order 9, कोई भी group ले लो, कितने भी groups हैं, you take any group of order 9, it is abelian. 16, 25, 36, 49, yeah or no? No, this is what the same thing I have done in class. Yes, p square where p is prime. Keep in mind this. So 16 is not allowed. Right? This is 4 square. 4 is not prime. We don't know about that. 36 similarly. We don't know about this. So 36 order ka group, all groups of order 36, we cannot say that they are abelian. There is a non-abelian group of order 36. There is a cyclic group of order 36, Z36. So that we cannot say. But what we can say, every group of order p square is abelian. 4, 9, 25, then 49, right, and so on. Okay, so before we prove this, we have let us say so we prove a result about the center. To prove a group is abelian, let us see that later. Let us first see this result. So let P be a prime, and G be a group of order p raised to n for some integer n. Right? So for some n belongs to n, we can say, let us say. So such a group is called P group, right? Such a group is called P group. What is a P group? P group is a group of order prime power. It's a group whose order is power of prime. Such a group is called P group. Right? Then, so G is a P group. So G, the power of G. So order of G is P power n for some n. Then what we have is Z of G. Center of G is always non-trivial. Remember, center is a subgroup. So center is always non-empty, identity always commutes with every element, so identity is always there. But when we see that, when we say that Zg is not equals to singleton identity, that means it contains an element other than identity, so it is non-trivial subgroup, right? So let us see the proof of this, right? So here we use this class equation, this version of class equation which we saw, right? So recall the class equation. How do we write this? Order of G equals to order of Z plus summation. We can write NA is not equals to G. Order of G upon order of NA. Okay, so, and what we are given? We are given equation of G. So G is a group. We are given order of G equals to P power n. This is what we are given. So P divides order of G, right? So NA is note that NA is a subgroup of G. So P, some power of prime, also divides order of NA. Again, let me say. So note that NA, normalizer of A, is a subgroup of G. So, and so by Lagrange's theorem, which is not necessary to mention, but just I am mentioning, order of NA divides order of G. It is understood now if I just say that order of NA is some power of prime. So order of G is P power n. So what could be order of NA? 1, P square, P cube up to P power n minus 1. It could be also P power n. Order of NA also can be equal to G. So then order of NA equals to P power Ka for some. P power K का form no होई ना, but P power Ka I have written because it depends on A. If I change A, I have another subgroup for that A, Na. So for some Ka less than equals to n. Yes, it can be also equals to n also, but we are interested in when Na K is strictly less than n. Kya strictly less than n thase? When it is equal to n, K equals to n, that means it also has order P power n. That means Na equals to G. We are interested in Na is not equals to G. This term we are interested in. So if Na is a proper subgroup of G, right? So if Na is a proper subgroup of G, then Ka is order of Na is I can say that it is P power Ka, where Ka is strictly less than n. Right? In that case, Ka is strictly less than n, and therefore, then we can say that P divides order of G upon order of Na. Right? So P divides order of G upon order of Na. Why? Because order of G upon order of Na क्या होगा? This will be P power n upon P power Ka. So this is P power n minus Ka. And what we have is Ka is strictly less than n. Right, so therefore numerator has more power of prime than the denominator. It can never be equal. So n minus Ka, this term, is greater than equals to 1. So at least one power of prime divides. So P divides this. And so P divides for all such proper subgroup whenever Na is not equals to G. So then P divides whole sum. wherever NA is not equals to G, P divides order of G upon order of NA. This is what we can conclude. But also P divides order of G, because order of G is what? Order of G is P power n. So P divides order of G, P divides this, and so we know that if P divides A, P divides B, then it divides their sum, it divides their difference. So therefore P divides their difference. So I can say that P divides order of G minus summation NA not equals to G order of G upon order of NA. So P divides the difference. Right? What we have used is this: P divides A, P divides B. This implies P divides A minus B. So P divides order of G. This is A. Right? So this is my A, and my this term is B. So P divides the difference. And so by class equation, what is order of G minus this sum? So if you see the class equation, yes, here. So order of G minus this sum goes this side, so it will give us order of ZG, right? So that means so P divides order of ZG, but order of ZG is greater than 0. Since order of ZG is greater than 0, P 0 को भी divide कर सकता है ना? Every number divides 0, but order of ZG is greater than 0, so 0 is not the case. So it cannot be 1, because prime cannot divide 1, and P divides order of ZG. We conclude that we can say that ZG is order of ZG is not equals to 1. Right? 0, no, nothing. It is positive, and P some prime divides the order, so order cannot be 1, and hence ZG is non-trivial. So order is not 1, so it is not singleton identity. There will be an element of in the center other than identity. So whenever G is a P group is just a power of prime. So whenever G has this, their center is always non-trivial. Even if you take non-abelian group, for example, quaternion group of order 8, 2 cube, but in a center ma identity सिवाय एक element तो हसे which commutes with all. So find that element other than identity. Which element it is? Take quaternion group. You know that plus or minus 1, plus or minus I, plus or minus j, plus or minus k. 8 elements, and ij equals to k in that cyclic order. Kj equals to I, and I square, j square, k square, those are equals to minus 1. Right? So that group, you know, it is 2 cube, so it is power of prime. The order is it fits into this. Take p equals to 2, n equals to 3, so it is of this form. What it says, center ma identity 1 cy, identity of there is 1 in quaternion group. 1 cy bijo element hase, so find that element. Okay, so when this is done, as a corollary we have, that is first application, every group of order p square is abelian. Right? So this is the first application, and we have to show that the group is abelian. So we start with, let G be a group with order of G equals to p square, where p is prime. So we have to show that G is abelian. So now there are two ways to show that the group is abelian. Right? So two ways. Don't write like this, I am just explaining. So two ways to show that the group is abelian. One way is this: we show that every element, every pair of elements in G commutes. So xy equals to yx for every xy in G, direct method. Another one is we show that zg equals to G. Right? What is zg? Zg is all those x in G which commutes with every y in G. So for every y in G, xy equals to yx. All those x which commute with every y in G. So if we show that each x belongs to Zg, if we show that G equals to Zg, that means every element belongs to Zg. That means every x commutes with every y. So every two elements of the group commute. So that shows that G is abelian. So there are two ways to show that a group is abelian. And so let us put this in the box. This is not to be written, but just I am explaining that sometimes the direct technique doesn't work. Right? What happens is that we don't have any idea about the group, so we don't know how two elements commute or not. There is by contradiction also we don't know whether this will be true or not. So this is the way we'll show that this by this method, second one. So this is helpful in problem solving also when we are trying to prove some group is abelian. Sometimes this method does not apply directly, so we try to show using center. So we prove that, we show that G is abelian. Using this, right? So since Zg, center is a subgroup, right? So Zg is a subgroup of since Zg is a subgroup of G and order of G equals to P square. What we have, or what is order of Zg? What are the possibilities? Subgroup. So by Lagrange's theorem, order of subgroup divides order of group. So it is either 1 P square. So 1 or P or P square. But this is not possible. Why it is not possible? So by above theorem, by above lemma or whatever, by above result, what we know is what we have just seen, that if G is a P group, if G is a group of order P power n, then center is non-trivial. Center does not have order 1. So here we have P square, n equals to 2. Right? Order of G equals to P square, so n equals to 2. By above result, Zg is non-trivial, and therefore, and so order of Zg cannot be equals to 1. So it is not 1. So order of Zg equals to P and P square. So but if order of Zg is P square, then we are done. If this is the case, then we are done. So let me write that. So if order of Zg equals to P square, this will be order of G, then Zg equals to G, and hence G is abelian. So in this case we are done. If it is P square, we are through. So only possibility now what remains to check is this, whether the order will be P or not. If it is P, then we should get some contradiction. So we should, yes, we should show that it is not possible that order is P. So suppose if possible, order of Zg, order of Z equals to, I have written Zg everywhere. Okay, so let me write Zg. You can write Z also. Z of G is not always necessary to write like this. It is. Then Zg is a proper subgroup of G. Zg is a proper subgroup of G. So we can say that if it is proper, then what we can say is there is an element in G which is not in Zg, because order of G is P square, as we have seen here. Order of G is P square, and this is P. So there is an element in G which is not in Zg. So let A belongs to G such that A is not in Z. Right? So A is, suppose A is an element which is in A does not belongs to ZG, which is in G but it is not in ZG. So now consider NA. If B belongs to ZG, right? So now B belongs to ZG. कोई element ZG में होए तो શું થાય? That means BX equals to XB. It commutes with every element of G, right? For all X in G. So then we can write this as BA equals to AB, because if it commutes with every element, so in particular it commutes with A, in particular X equals to A. So that means B belongs to NA, right? If B commutes with A, then B belongs to NA. So we started with B belongs to ZG. No, this is not the way. It should not double imply. Yeah, B commutes with A only. It's not necessary that B commutes with every. So this is the way we are going. So that means ZG. So ZG is a subset of NA. If an element is in ZG, it is in NA. Why? Because if it is in ZG, it is in the center, it commutes with every element, so it commutes with A. So it is in normalizer of A. But normalizer A no element hoy to bada element સાથે commute કરે. There is no guarantee. Only we know that it commutes with A. Okay, but okay, can we show that this is proper subset? Yes, this will be proper subset because A belongs to NA. A to A સાથે commute કરે જ ને. A equals to A. So A belongs to NA and A does not belongs to ZG. એવો તો આપણે element લીધો છે. We have taken an element here which is not in ZG, but it is in NA. A belongs to NA. Right? A belongs to NA. So what does this give us? So ZG is it's a subset of NA. Not only that, it's a proper subset of NA. And if it is proper subset, that means number of elements in ZG is strictly less than number of elements in NA, and hence we have. So we have order of ZG strictly less than order of NA, because NA is subgroup. It is less than order of G. But then this implies what is order of ZG? Order of ZG, we have assumed it is P. Suppose if possible, order of ZG is P in this case. Right? So this is P. Order of NA we don't know. Order of G is P square. So now only possibility for order of NA, since NA is a subgroup, it's a subgroup of G. What are order of NA? Order of NA equals to 1 P or P square. It divides order of group, but it is not 1. It cannot be 1. It cannot be P, because it is strictly greater than P. So from this, what we get is order of NA equals to P square equals to order of G. But then this implies NA equals to G, and look where we started that lemma. NA equals to G if and only if A belongs to ZG. So this, at least I can write A belongs to ZG. Here I can write if and only if, because this part it is if and only if. But let us not go that. We have just A belongs to Z, A belongs to ZG, which is a contradiction. It is a contradiction. Right? This one we are getting A in ZG, but we started with A is an element which is not in ZG. So we have this is not possible. So order is this is not possible. This is also not possible. So order of ZG equals to P is also not possible. So the only case we have order of Zg equals to P square equals to order of G, and so G is abelian. Right, so this is the first application which we have done, that every group of order P square is abelian. What we used the fact that we proved first that if G is a P group, that means if order of G is power of prime, then the center is always non-trivial. So that we have seen, and now second application, that is Cauchy's theorem. We have done this in the first unit for abelian groups, finite abelian groups we have done. Of course, it is true only for finite groups. We are saying P divides order of G. So application number 2, that is Cauchy's theorem. So what was the result? Result is let G be a group and P be a prime such that P divides order of G. G be a group and P is a prime such that P divides order of G. Of course, it is when we say group here, it is finite because P divides order of G. Then G has an element of order P. So if you recall, in the first unit we have seen that there exists A in G. A in G, A is not equals to identity, and A raised to P is identity. So A raised to P is identity. The P is the smallest integer such that A raised to P is identity. That means order of A is P. So this implies order of A is P. G has an element of order P. So this is the meaning. And we have proved this result already for abelian groups. So recall that. We already proved this result. Now it is in general. Now we are not saying non-abelian, abelian, not saying anything. It is general. Just G is any group. We have proved this result for finite abelian groups. Right, now we prove this one for arbitrary group. Right, so we, as in that case, we also prove this same result by induction. So we prove this result by induction on order of G. So first case, order of G equals to 1. There is nothing to prove. Better way to write the result is vacuously true. So in that case, in this case, we do not have any prime which divides order of G. So if there is a prime which divides order of G, we have to produce an element of that order. 2 divides order of G, we have to find an element of order 2. 3 divides order of G, we have to find an element of order 3. 5 divides order of G, we have to find an element of order 5. If 12 divides order of G, no, 12 is not a prime, so we don't know about that. So this is for only primes. Right? So if order of G is 1, then result is vacuously true. That means there is nothing. Vacuously means there is no prime which divides 1. So we are done in this case. And we have induction hypothesis, in which we assume that suppose the result is true for all groups whose order is strictly less than order of G. Right? So assume that the result is true for all groups with order strictly less than order of G. So we assume the result is true for all the groups whose order is strictly less than order of G. This is how we do in induction, right? We take n equals to 1 then we assume that it is true for 1 to n minus 1, or 1 to n, then we go for n plus 1. So suppose order of G is n, then result is true for up to 1 to n minus 1. And now we have two cases. So first case, P divides order of a proper subgroup of G. So let us consider two cases. P divides order of a proper subgroup of G. Right, so that means let W be a subgroup of, let W be a proper subgroup of G. W be a proper subgroup of G, and P divides order of W. So since W is proper, because it is proper subgroup of G, we have order of W is strictly less than order of G. So these two conditions are satisfied. You see, P divides order of W, and W order of W is strictly less than order of G. So this is true. So by induction hypothesis, we say that W has an element of order P. By induction hypothesis, there exists A in W, which is in G. Of course, W is subset of G. Let me not write right now. A in W such that order of A is P. So A belongs to W is subset of G. Right. So A is an element, that is G has an element which is A of order P. So in this case we are done, very easy, because if we can go to the from the nth case to n minus 1 case, or to the lower case with the condition, this condition that P divides order of W, then we are easily we apply induction hypothesis. But suppose this may not be the case. So what is the second case? P does not divide order of any proper subgroup of G. या तो proper subgroup હોય જ નહીં, એવું તો નહીં થાય આ કેસમાં. Subgroup of G. P does not divide order of any proper subgroup of G. If this is the case, then what we use is the class equation, and it is again the same technique what we apply. So recall the class equation of G in this case. Recall the class equation of G. What is that? So order of G equals to order of Z plus, so those ones we have separated out, that I have written separately. NA is not equals to G, order of G upon order of NA. Right, so now NA is a subgroup of G, so and NA, if NA is a proper subgroup of G, then so in case if NA is a proper subgroup, NA subgroup to thase, it is proper subgroup or it is equals to G. So when NA is a proper subgroup of G, then P does not divide order of NA. Why? This is because by our case, this is what we have assumed. Right, this is our case. We have assumed that P does not divide order of any proper subgroup of G. So if NA normalizer of A is a proper subgroup of G, then P does not divide order of NA. But P divides order of G. This is given. Right, statement માં જેવું છે Cauchy's theorem માં. Suppose G is a group and P divides order of G. So this is given. So that means then P divides order of G upon order of NA when NA is a proper subgroup. of G. So if NA is proper subgroup, it divides, P divides the numerator, order of G, but P does not divide order of NA, so it does not divide denominator, so there is, P does not get cancelled out from numerator and denominator, so prime to us divide करसे even, and this is an integer. Why it is an integer? Because NA is a subgroup, so order of subgroup is a divisor, so divisor, so this is divisor of order of G, so order of G upon this divisor is again an integer, so P divides order of G upon order of NA, so we have this, and now this is true for all this NA, right? It is true for all such NA, so this implies P divides summation whenever NA is proper, that means whenever NA is not equals to G, it divides order of G upon order of NA. And because P divides order of G, so it divides the difference. Again, same જ વસ્તુ આપણે પહેલા પણ કરી હતી, same thing. I need to add a page here, okay. And so since P divides order of G, we have, so P divides A, P divides B, so P divides A minus B. So P divides A minus B, order of G minus summation NA is not equals to G, order of G upon order of NA. So by class equation, what is going to be this? This is going to be order of Z. So by class equation, we have P divides order of Z, and Z is a subgroup of, should not write this, okay, we all know the subgroup. So P divides order of Z, so what can we say? We are in which case? P does not divide order of any proper subgroup of G, but Z is a subgroup of center, ZG is a subgroup of G, but P तो એને divide ना करવું જોઈએ जो proper હોય तो. But what we are getting, P divides order of Z, so by our assumption, in this case, we have assumed that P does not divide order of any proper subgroup, but here P divides order of G, so by our assumption in this case, P, we can say that Z is not a proper subgroup of G. So proper subgroup now, so what is the possibility? Z is trivial or Z equals to G, but this is not possible. Right? This case is not possible because P divides order of Z, so it is not trivial. So hence Z equals to G. Therefore G is abelian. So by Cauchy's, but G is abelian, we have already proved. If G is an abelian group, P divides order of G, then there is an element in G of order P. This is already proved in unit 1. So by Cauchy's theorem for abelian groups, the result follows. In abelian case, we already done. So by Cauchy's theorem for abelian groups, the result follows. So in this case, we are done. Okay, I stop here for now, and then there is only one lecture remaining, which we'll cover in the next video, and then this unit will be over.